Welcome to our channel. We are so glad you found your way here. Let us help you fall asleep. Let's begin with the first stars, lighting up the universe's dark ages. Take a slow, deep breath in and release it. Let the weight of the day fade away as we embark on an unhurried, atmospheric journey through the wonders of the cosmos. Your mind is quiet, the universe is vast, and we are ready to explore. A profound stillness enveloped the cosmos during the cosmic dark ages, a period preceding the birth of the first stars. This era, spanning approximately 500 million years after the Big Bang, saw the universe in a state of primordial simplicity. Intergalactic space was filled with hydrogen and helium, along with trace amounts of lithium, but none of the luminous entities that would later populate the night sky. Without the radiance of stars to illuminate the vast expanses, darkness reigned supreme. This absence of light fostered a unique environment, characterized by a cold, dense fog of gas and dust. The temperatures hovered just above absolute zero, creating a hostile landscape where the only interactions involved the faint remnants of cosmic microwave background radiation. Amidst this obscurity, gravitational forces began to play a pivotal role. Over time, slight density fluctuations within the primordial gas led to the gradual accumulation of matter. Regions of higher density experienced gravitational collapse, setting the stage for the formation of the first structures in the universe. These nascent clumps of gas, still hidden from view, were poised to ignite the first nuclear fusion reactions. As these conditions progressed, the stage was set for the eventual emergence of light. This transformative moment would mark the end of the Dark Ages and herald the dawn of a new era in cosmic history. These elements, hydrogen and helium, served as the building blocks of the cosmos. Formed in the first few minutes after the Big Bang, they constituted nearly 98% of all baryonic matter. In this primordial landscape, hydrogen dominated, existing primarily in its simplest form, while helium formed from the fusion of hydrogen nuclei under extreme temperatures and pressures. In the absence of heavier elements, these light atoms played a crucial role in the formation of the early universe. Regions of higher density began to coalesce, influenced by gravitational forces, gradually giving rise to the first stellar structures. The fusion processes initiated within these nascent stars would forge heavier elements over time, enriching the surrounding medium. Radiation produced during the formation of these stars contributed to the reionization of the universe. Photons emitted from their surfaces began to impact the surrounding hydrogen gas, stripping electrons from their nuclei and transforming the neutral hydrogen into a plasma state. This transition illuminated vast regions of space, effectively ending the long period of darkness. As these stars evolved and radiated their energy, they played a pivotal role in the formation of the first atoms. During the recombination era, which occurred approximately 380,000 years after the Big Bang, the universe underwent a significant transformation. Photons, previously trapped in a dense fog of charged particles, began to travel freely through space, as electrons combined with protons to form neutral hydrogen atoms. This process marked a critical moment in cosmic history. The temperature of the universe decreased to about 3000 Kelvin, allowing for stability in atomic structures. As electrons coalesced with protons, the intricate balance of forces initiated a ripple effect, reducing the opacity of the universe. Light could now permeate the vast expanses, leading to the decoupling of matter and radiation. The emergence of neutral hydrogen atoms paved the way for the formation of the first structures. Regions of slightly higher density began to collapse under their own gravity, giving rise to the first galaxies and clusters. This expansion was not uniform. Small fluctuations in density created a mosaic of varying gravitational wells, setting the stage for the intricate cosmic web that would later form. Though the universe was still predominantly dark, the seeds of complexity had been sown, laying the foundation for the diverse array of cosmic phenomena that would unfold over billions of years. Fleeting remnants of those formative moments can be detected in the cosmic microwave background radiation. This pervasive afterglow, a relic from approximately 380,000 years post-Big Bang, permeates the universe, providing critical insights into its infancy. It represents the moment when the hot, dense plasma of the early universe transitioned into a transparent state, allowing photons to travel freely for the first time. This radiation is remarkably uniform, with slight temperature fluctuations that serve as signatures of the primordial density variations. These minute irregularities, mere 1 part in 100,000, are the echoes of the initial density fluctuations that would give rise to galaxies and larger structures. By meticulously analyzing this radiation, astrophysicists glean information about the universe's composition, geometry, and expansion rate. The imprint left by those early epochs is essential for understanding how the universe evolved into its current state. Such evidence not only illuminates the conditions that led to the formation of the first stars, but also provides a timeline of cosmic history. The faint light, traveling across vast expanses, serves as a bridge between the distant past and the present, offering a glimpse into the universe's transformative journey through time. The influence of dark matter on structure formation is profound and pervasive, shaping the very fabric of the universe. Invisible and elusive, it comprises a significant portion of the cosmos, exerting gravitational forces that mold the distribution of visible matter. This unseen entity acts as a scaffold for galaxies, clusters, and larger cosmic structures, guiding their formation and evolution. Within this region, gravitational wells created by dark matter pull in gas and dust, sparking the birth of stars and galaxies. As time progresses, these structures grow increasingly complex, forming intricate webs that weave through the cosmos. The gravitational interactions between the clumps of dark matter dictate not only the location of galaxies, but also their movement and behavior across cosmic time. Observations reveal that this distribution of dark matter aligns with the visible matter, suggesting a deep interconnectedness. Structures coalesce around dense concentrations, allowing luminous objects to thrive in the dark. The cosmic microwave background radiation provides further evidence, indicating fluctuations that correlate with the density of dark matter just after the Big Bang. In essence, dark matter's silent governance orchestrates the universe's expansion and contraction, continuously influencing the gravitational dance of celestial bodies, laying the groundwork for the vibrant cosmos observed today. Density fluctuations, a result of the gravitational interplay initiated by dark matter, play a pivotal role in the formation of the first stars. Regions with slightly higher concentrations of matter experience gravitational collapse, pulling surrounding gas and dust inward. This process creates a dense core, where temperature and pressure rise progressively, setting the stage for nuclear fusion. The primordial gas, primarily composed of hydrogen and helium, accumulates within these collapsing regions. As it condenses, it heats up, reaching critical temperatures necessary for fusion processes to ignite. This transformation marks the birth of a new star, illuminating the surrounding darkness of the universe. These early stellar formations, often referred to as population 3 stars, are characterized by their massive size and short lifespans. Once ignited, these stars emit vast amounts of energy, providing the first sources of light in a previously dark cosmos. Their radiation influences nearby gas clouds, triggering further collapses and subsequent star formations in a cascading effect. This sequence initiates the evolution of galaxies as groups of stars begin to coalesce under the influence of gravity. The life cycle of these early stars is marked by explosive supernovae, which disperse heavier elements throughout the universe, enriching the surrounding medium. These elements will eventually play a crucial role in the formation of planets and the first generation of stars, known as population 3 stars, emerged from primordial gas clouds composed mainly of hydrogen and helium, lacking the heavy elements produced by earlier stellar generations. These celestial bodies were remarkably different from those that followed. Their formation marked the beginning of light in an otherwise dark universe, igniting the cosmic environment with energy and radiation. These stars were massive, often exceeding 100 solar masses, and their lifespans were relatively short, typically lasting only a few million years. The intense pressure and temperature at their cores initiated nuclear fusion, converting hydrogen into helium and subsequently generating heavier elements through stellar nuclear synthesis. Upon exhausting their nuclear fuel, these stars ended their lives in extraordinarily powerful supernova explosions. The death of population 3 stars resulted in the dispersal of newly formed elements into the surrounding interstellar medium. This process enriched the gas clouds, setting the stage for the formation of the next generation of stars, known as population 2. These subsequent stars began to incorporate the heavier elements produced by their predecessors, leading to a richer and more complex chemistry throughout the universe. This evolution of stellar populations is crucial for understanding the transition from the cosmic dark ages to a more illuminated epoch filled with galaxies, clusters, and the intricate structures that characterize the observable universe today. Quantum fluctuations played a pivotal role in the formation of those early stars. In the vast emptiness of space, these minute variations in energy levels emerged, providing the necessary seeds for gravitational instabilities. When regions of slightly higher density formed, they began to attract surrounding matter, gradually accumulating gas and dust. This process unfolded over millions of years, as these primordial clouds collapsed under their own gravity. The interplay between quantum mechanics and gravitational forces facilitated the emergence of the first protostars. As these dense regions continued to condense, temperatures soared, igniting nuclear fusion at their cores. The initial release of energy marked the birth of stars, casting light into the surrounding darkness, altering the fate of the cosmos. The first stars, composed predominantly of hydrogen and helium, emitted ultraviolet radiation that began to ionize the surrounding interstellar medium. This ionization influenced subsequent star formation, creating bubbles of hot gas that expanded and interacted. The energetic feedback from these early luminous bodies affected the dynamics of their local environments, pushing and pulling on surrounding material. This intricate relationship between quantum fluctuations and stellar evolution laid the groundwork for the complex structure of galaxies. Understanding these processes reveals the interconnectedness of physical phenomena that shaped the universe's history, illuminating the path from chaos to cosmic order. Theoretical models of early star formation offer insight into the mechanisms that governed the creation of the first luminous objects. Simulations depict vast clouds of gas and dust collapsing under their own gravity, reaching critical densities. These regions, known as molecular clouds, serve as the birthplace of stars. The intricate interactions between gas particles lead to the formation of protostars, which begin to heat up as gravitational potential energy converts into thermal energy. Predictions suggest that the first stars were predominantly massive, with masses exceeding 30 times that of the Sun. Such characteristics stem from the low metallicity present in primordial gas, resulting in less efficient cooling processes. As these massive stars ignite, They release tremendous energy and commence nuclear synthesis, forging the basic elements that will eventually form galaxies and planetary systems. Simulations further indicate that the feedback mechanisms from these stars, including stellar winds and supernova explosions, play a crucial role in shaping their environments. They influence the subsequent formation of stars and galaxies, contributing to the evolution of cosmic structure. The interplay of these forces culminates in a complex web of interactions, where massive stars give rise to new stellar generations. This continuous cycle of creation and destruction lays the foundation for modern astrophysical phenomena, connecting the distant past with the present universe. The role of metallicity in stellar formation is critical. This parameter, which refers to the abundance of elements heavier than hydrogen and helium, profoundly influences the characteristics of new stars. In primordial gas clouds, those lacking metals, temperature and density conditions determined the initial stages of star formation. Without the presence of these heavier elements, the thermodynamics of collapse differ significantly, leading to the creation of massive stars that ignite with greater intensity. In regions enriched by supernovae, the introduction of metals alters the cooling processes within molecular clouds. This enhancement results in increased fragmentation, enabling the formation of smaller, more diverse stars. The presence of these elements allows for the formation of planets and other celestial bodies, creating a rich environment for potential life. Metallicity also affects the lifespan and evolution of stars. Higher metallicity can lead to more efficient cooling, influencing the dynamics of nuclear fusion within a star's core. This process, the interstellar medium infused with elements from previous generations, acts as a reservoir for future stars. This ongoing exchange informs the future of galactic evolution, illustrating the intricate connections between past events and the ongoing cycle of stellar birth and death. The life cycle of population 3 stars begins deep within primordial gas clouds, primarily composed of hydrogen and helium. These clouds, under the influence of gravity, collapse over time, leading to immense pressure and temperature at their cores. Conditions become ripe for nuclear fusion, igniting the process that fuels these stars. They emerge as massive entities, often exceeding 100 times the mass of the Sun, characterized by their intense brightness and heat. Once formed, these stars evolve rapidly due to their large mass, burning through their nuclear fuel at an extraordinary rate. Stellar winds expel material into the surrounding space, enriching the interstellar medium with heavier elements. This phenomenon transforms the environment, creating the conditions necessary for subsequent generations of stars to form. Eventually, as they exhaust their fuel, these colossal stars reach the end of their life cycles. The core collapses under its own gravity, while the outer layers are expelled in a tremendous explosion known as a supernova. This event is not merely a violent conclusion, but a critical moment in cosmic evolution. It disperses elements across vast distances, seeding the universe with the building blocks for future stars, planets, and potentially life itself. Each supernova contributes to the ongoing narrative of cosmic creation, illustrating the profound interconnectedness of stellar life and death. During the brief moment known as cosmic inflation, the universe underwent a rapid expansion, stretching the fabric of space-time itself. This event, occurring mere fractions of a second after the Big Bang, served as the catalyst for the formation of all structures that would later populate the cosmos. Within this infinitesimal period, fluctuations in energy density created the seeds for galaxies, clusters, and vast cosmic filaments. Tiny quantum variations in this expanding expanse manifested as slight density differences, These irregularities laid the groundwork for gravitational attraction, guiding matter toward clumping together. As the universe cooled, hydrogen and helium formed, allowing the first structures to emerge in this young universe. The significance of inflation extends beyond mere expansion. It set the initial conditions necessary for the universe's evolution. The temperature and density fluctuations influenced the formation of the cosmic microwave background radiation, a relic of the universe's infancy. This afterglow, permeating the entire cosmos, offers a glimpse into the conditions present shortly after inflation halted. Observational tools such as the Planck satellite and various ground-based telescopes have provided exquisite detail on these ancient fluctuations. They reveal an intricate pattern that continues to inform our understanding of cosmic evolution. Each discovery from this period deepens the comprehension of how structure formed in the universe, guiding scientific inquiry into its ongoing development. Baryonic matter serves as a fundamental building block in the formation of stars, interacting with dark matter to create gravitational wells. In these regions, density increases as gas and dust coalesce under their own weight, laying the groundwork for stellar birth. This process is influenced by the cooling mechanisms of the gas, primarily through radiation, enabling it to condense into denser clumps, which eventually ignite nuclear fusion. The interplay between baryonic matter and dark matter can be seen in the formation of primordial gas clouds. These clouds, primarily composed of hydrogen and helium, possess the necessary conditions for star creation. As these gases collapse, they fragment into smaller clumps, allowing for multiple star systems to emerge from a single molecular cloud. The efficiency of star formation is also contingent upon the environment, such as the presence of shock waves from nearby supernovae, which can trigger further collapse. Once a protostar forms, it begins to heat up, eventually leading to nuclear reactions in its core. The energy produced pushes back against gravitational collapse, achieving a delicate balance that defines a star's life cycle. This feedback mechanism has implications for subsequent star formation, affecting the chemical composition of the surrounding medium and contributing to the evolution of galaxies. The presence of baryonic matter thus remains crucial in the cosmic narrative of star formation and evolution. The formation of the first galaxies represents a pivotal moment in cosmic history. Drawing from the primordial gas present after the Big Bang, these dense regions initiated gravitational collapse. Over time, the accumulation of hydrogen and helium created the necessary conditions for star formation. As this process unfolded, clumps of gas began to cool, allowing for the development of the first stellar bodies. Within these nascent galaxies, stars ignited, marking the end of the cosmic dark ages. Their light illuminated the surrounding environment, dispersing the dense fog of neutral hydrogen that had dominated the early universe. This interaction catalyzed further cosmic evolution, as ultraviolet radiation from young stars influenced the ionization state of nearby gas. The early galaxies were not uniform. Variations in density led to diverse structures, including spirals, irregulars, and ellipticals. Mergers and interactions between these forming galaxies played a significant role in shaping their characteristics. These encounters would forge new stars and trigger bursts of star formation, producing heavier elements that subsequently enriched the interstellar medium. These developments laid the groundwork for the intricate architecture of the universe as it is observed today. The first galaxies served not only as stellar nurseries, but also as the building blocks for larger cosmic structures, paving the way for the vast array of galaxies that populate the cosmos. Evidence of the first stars remains elusive, shrouded in the vastness of time and space. Observational challenges arise from the faintness of these ancient beacons, which formed during the universe's infancy. Light from these stars, emitted over 13 billion years ago, is significantly redshifted, blending into the cosmic background noise. Detecting their signatures demands extraordinary sensitivity from advanced telescopes designed to peer into the distant past. This region of the universe where the first stars ignited is characterized by a low density of matter compared to later epochs. The intergalactic medium, predominantly composed of hydrogen and helium, absorbed much of the radiation, complicating efforts to trace the light emitted by these early luminaries. Consequently, astronomers rely on indirect methods, such as the examination of distant quasars, to infer the presence of these stars. Spectroscopic analysis reveals the chemical fingerprints of primordial elements, providing tantalizing clues about the conditions of the early universe. Observations from instruments like the James Webb Space Telescope are beginning to illuminate this dark period, capturing glimpses of the first galaxies and their stellar populations. While direct observation remains challenging, these efforts pave the way for a deeper understanding of the universe's formative years. The history of cosmic reionization illustrates a pivotal transition in the evolutionary timeline of the universe. Initially, the cosmos existed in a state of neutrality, dominated by hydrogen and helium atoms, with vast stretches of darkness enveloping the early universe. The absence of light created a cold, opaque environment, inhibiting the movement of photons across great distances. As star formation commenced, the first luminous entities emerged from dense regions of gas, igniting a profound transformation. These nascent stars fused hydrogen into helium, releasing immense amounts of energy in the form of ultraviolet light. This radiation played a crucial role in ionizing surrounding hydrogen atoms, stripping electrons away and creating free protons. The process of reionization unfolded over several 100 million years, with clusters of stars forming in various locations, gradually illuminating vast regions of space. As more stars ignited, the universe transitioned from a dark, dense state to one filled with light and ionized gas. The aftermath of this reionization period saw the formation of galaxies, clusters, and the intricate structures that populate the universe today. The cosmic web that emerged, connecting galaxies and regions of space, became a hallmark of the universe's evolution, allowing light to travel freely. This marked the dawn of a new era, shaping the cosmic landscape in ways that continue to influence the universe's development. Nuclear fusion emerged as the fundamental process powering these early stars. Within their cores, immense gravitational pressure generated temperatures exceeding millions of degrees, facilitating the fusion of hydrogen nuclei into helium. This process released vast quantities of energy in the form of light and heat, illuminating the surrounding darkness of space. The fusion reactions not only provided the energy needed to sustain the stars against gravitational collapse, but also initiated the complex network of chemical elements that would later enrich the universe. In these nascent celestial bodies, the balance between the outward pressure from fusion and the inward pull of gravity dictated their life cycles. This equilibrium allowed them to shine brightly for millions of years, creating localized areas of enhanced luminosity in the vast cosmic expanse. The intense heat forged heavier elements through subsequent fusion processes, such as carbon and oxygen, laying the groundwork for future stellar generations. As they reached the end of their lifespans, many of these stars underwent supernova explosions, dispersing their enriched materials across the cosmos. This scattering of elements contributed significantly to the formation of new stars and planetary systems. The light generated by the fusion process not only marked the end of the universe's dark ages, but also heralded the beginning of a rich and diverse cosmic tapestry, forever altering the fabric of existence. The emergence of early stars significantly transformed their surrounding environments. These massive luminous bodies emitted intense radiation, which ionized the hydrogen gas prevalent in the cosmos. This process initiated a series of complex interactions that affected the structure and composition of nearby regions. The heat generated by this stellar activity drove away cooler gas and dust, creating vast bubbles in the interstellar medium. In this newly energized environment, the formation of subsequent stars was influenced by the altered densities and temperatures. Gravitational forces became more pronounced, encouraging the clumping of material and leading to new stellar births. The chemical enrichment introduced by supernova explosions further modified these regions, infusing heavy elements into the primordial hydrogen and helium. With each successive generation of stars, the dynamics of galaxies began to evolve. These stellar giants influenced the formation of structures on a grand scale, leading to the creation of the first galaxies. Their light began to illuminate the universe, marking a pivotal transition from darkness to a cosmos filled with brightness and complexity. The delicate balance between radiation pressure and gravity played a crucial role, shaping the paths of stellar evolution. Over eons, this interplay sculpted the very nature of cosmic evolution, setting the stage for the rich diversity of galaxies observed in the current universe. Feedback mechanisms emerged as these early stars ignited, exerting profound influences on their surroundings. Intense radiation and stellar winds from these luminous bodies transferred energy to the surrounding gas and dust, triggering complex interactions. This region became a crucible of transformation, where the remnants of stellar life cycles contributed to the chemical enrichment of the interstellar medium. Supernova, the explosive deaths of massive stars, released vast quantities of energy and heavy elements into space. This process not only recycled material, but also generated shockwaves that compressed nearby gas, fostering the birth of new stars. Such cyclical behavior established a dynamic equilibrium, allowing for ongoing star formation while simultaneously regulating the growth of galaxies. Temperature fluctuations and density variations within this medium influenced the gravitational collapses that birthed subsequent generations of stars. The interplay of radiation pressure and gravitational forces created a delicate balance, facilitating the emergence of increasingly complex structures. In these early epochs, the universe began to evolve from a largely homogeneous state to one marked by intricate filaments and clusters. Each generation of stars played a pivotal role in shaping the chemical landscape, leading to the formation of planets and potentially life. Thus, feedback mechanisms became foundational elements in the architecture of the cosmos, intricately linking stellar activity with the larger cosmic narrative. The emergence of heavy elements marked a pivotal transformation in the universe's chemical landscape. Within the cores of massive stars, nuclear synthesis occurs under conditions of extreme temperature and pressure. This process initiates the fusion of lighter elements, such as hydrogen and helium, into heavier ones, including carbon, oxygen, and iron. Such reactions are responsible for the enriching of the interstellar medium, where stellar winds and supernovae disperse these newly forged elements across vast distances. In their final stages, these massive stars often undergo gravitational collapse, culminating in a supernova explosion. This cataclysmic event not only expels the remnants of the star, but also creates even heavier elements, including gold and uranium. The remnants scatter into surrounding regions, contributing to the next generations of stars and planets. This cycle of birth, life, and death fosters a complex cosmic ecosystem. The presence of heavy elements paves the way for the formation of rocky planets and the complexity required for life. As these elements coalesce in gas clouds, the building blocks for future solar systems emerge, revealing the interconnectedness of the cosmos. The delicate balance achieved through nuclear synthesis illustrates the profound influence that these stellar processes exert on the evolution of the universe. Each generation of stars enriches the cosmic landscape, shaping the very fabric of existence. In this vast expanse, The transition from population 3 to population 2 stars marks a pivotal moment in cosmic history. Initially, population 3 stars emerged, formed from primordial gas and devoid of heavy elements. These ancient giants, massive and luminous, forged the first elements within their cores, a process that would profoundly alter the chemical makeup of the universe. As these stars reached the end of their life cycles, their explosive deaths in supernova events dispersed newly created elements into the surrounding space. This seeding of heavier elements enabled the formation of population 2 stars, characterized by lower mass and a richer chemical composition. These stars ignited in regions enriched by the remnants of their predecessors, illuminating the dark voids that once remained untouched. The emergence of population 2 stars heralded the birth of galaxies, creating structures that would serve as the cradle for future stellar generations. In this new era, the star formation became more diverse and complex, reflecting the varied environments influenced by the remnants of supernovae. These stars, often found in globular clusters, exhibit different life cycles compared to their predecessors. Their evolution contributes to the ongoing cycle of cosmic rebirth, as they eventually contribute their own elements back into the interstellar medium, perpetuating the intricate dance of stellar evolution. Investigating the first supernova explosions reveals pivotal moments in the universe's evolution. These cataclysmic events marked the end of massive stars, unleashing tremendous energy and scattering newly forged elements across the cosmos. The immense luminosity emitted during these explosions illuminated the surrounding regions, transforming the previously dark expanse into a canvas of light and matter. The light from these early supernovae provides critical insights into the composition of the universe shortly after its inception. Elements such as carbon, oxygen, and iron were synthesized in the cores of these massive stars, only to be expelled into space at the moment of detonation. This dispersal enriched the interstellar medium, forming the building blocks for future generations of stars and planets. The remnants of these explosions are often observed as supernova remnants, which serve as laboratories for understanding high-energy astrophysical processes. Within these regions, shock waves propagate through surrounding gas, compressing it and triggering the formation of new stellar objects. The interplay between light and elemental distribution from these events sculpted the conditions necessary for the emergence of galaxies. Through the study of these early supernovae, scientists glean knowledge about the universe's age, expansion rate, and chemical evolution. The very fabric of existence weaves together the remnants of such powerful occurrences, echoing through cosmic time and space. The role of dark energy in cosmic evolution introduces profound complexities to the understanding of the universe. This enigmatic force, constituting approximately 70% of the cosmos, drives the acceleration of its expansion. Its influence permeates vast regions, shaping the very structure of space-time itself. As galaxies drift further apart, the implications of dark energy become increasingly evident, altering the fate of cosmic entities. Observations reveal that this energy opposes gravitational forces, creating a tension that governs the dynamics of celestial bodies. The expansion rate, once believed to be slowing, is now recognized as an accelerating phenomenon, attributing this unexpected behavior to the presence of dark energy. The interplay between this force and matter creates a delicate balance, determining the evolution of cosmic structures over billions of years. In this expanding universe, clusters of galaxies form and dissolve, while the remnants of ancient stars and stellar nurseries give birth to new generations of celestial objects. The distribution of dark energy plays a critical role in regulating the density of the cosmos, influencing the formation of both large-scale structures and the voids that punctuate them. Understanding dark energy remains one of modern astrophysics' most significant challenges, as researchers strive to unveil its nature and implications for the ultimate fate of the universe. This ongoing inquiry is vital to grasp the comprehensive narrative of cosmic evolution. The influence of cosmic rays from early stars shaped the primordial environment of the universe, These energetic particles, originating from the first generations of stars, permeated the interstellar medium, interacting with gas and dust to create a complex web of chemical processes. The presence of cosmic rays accelerated nuclear reactions, leading to the formation of elements beyond hydrogen and helium, enriching the surroundings with heavier elements essential for the emergence of galaxies. In this energetic arena, the interplay between cosmic rays and surrounding matter played a critical role in the cooling of gas clouds. As these clouds condensed, they became the sites of future star formation. The initial bursts of radiation emitted by the first stars influenced the temperature and density of nearby regions, facilitating the gravitational collapse needed for new stellar bodies to ignite. Cosmic rays also contributed to the ionization of hydrogen, altering the state of the surrounding gas. This ionization process created ionized regions, commonly referred to as H2 regions, where the intense radiation from young, massive stars influenced the evolution of their environments. These regions became crucial for the dynamics of galactic formation, establishing a foundation that would support the development of complex structures throughout the universe. The formation of early galaxies resulted in the emergence of dwarf galaxies, characterized by their small size and low luminosity. These structures, often composed of a few billion stars, played a pivotal role in the evolution of the cosmos. Concentrated in regions of high dark matter density, they served as gravitational anchors, influencing the surrounding interstellar medium and fostering conditions conducive to star formation. Dwarf galaxies typically exhibit irregular shapes, reflecting their turbulent histories, shaped by gravitational interactions with nearby larger galaxies. This irregularity, alongside their metal-poor compositions, provides insights into the primordial processes that governed star formation in the early universe. Many of these galaxies formed through the merging of smaller clumps of gas and dark matter, leading to the gradual accumulation of stellar populations. As time progressed, some dwarf galaxies became satellites of larger galactic structures, contributing their gas and stars to these more massive entities. This ongoing interaction facilitates a cycle of growth and recycling, enhancing the complexity of galactic formations. The study of these ancient galaxies reveals not only the mechanisms of star formation, but also the evolution of chemical elements as they transitioned from primordial hydrogen and helium to more complex structures. The remnants of these dwarf galaxies can still be observed today, illuminating the intricate processes that shaped the universe's early landscape. Active galactic nuclei emerged as pivotal players in the early universe's dynamics. These luminous centers, powered by supermassive black holes, served as beacons of energy during a period where darkness prevailed. Emitting vast quantities of radiation, they contributed significantly to the reionization of hydrogen, a process that transformed the cosmic environment around them. The intense gravitational forces at play within these nuclei facilitated the accretion of surrounding matter, leading to the emission of X-rays and other high-energy particles. This activity not only illuminated nearby regions, but also influenced the formation and evolution of galaxies. The radiation from active galactic nuclei acted as a catalyst, regulating star formation and impacting the distribution of gas within the surrounding galaxies. Within these early structures, interactions among galaxies became more pronounced, resulting in mergers and collisions that reshaped their architecture. The energy output from these active centers played a critical role in clearing out the remaining cosmic fog, allowing light from the first stars to permeate through the universe. In this way, active galactic nuclei were not merely isolated phenomena, but rather integral components of a broader cosmic narrative, dynamically altering the landscape and fostering conditions conducive to the emergence of subsequent generations of celestial bodies. Their influence reverberated through the ages, shaping the universe as it transitioned from darkness to light. Advanced observational techniques have emerged to peer into the universe's infancy. Telescopes equipped with highly sensitive detectors capture the faintest signals emitted from these early stars, allowing scientists to gather crucial data. Ground-based observatories operate in tandem with space telescopes, enhancing the ability to detect and analyze light from distant celestial objects. Observations in the infrared spectrum play a vital role, as the heat signatures from these ancient giants reveal their presence amidst cosmic dust and gas. Gravitational lensing serves as another tool, exploiting the warping effect of massive objects to magnify the light from far-off stars. This technique unveils a clearer picture of their formation and distribution, offering insights into the conditions that fostered their birth. In addition, radio telescopes detect emissions from hydrogen, the most abundant element in the universe, which provides indirect evidence of the first stars and their influence on surrounding matter. Computer simulations complement these observational methods, creating models that predict the characteristics and behaviors of early stars. By comparing simulated data with actual observations, researchers refine their understanding of how these celestial bodies ignited the cosmos and paved the way for subsequent generations of stars and galaxies. Each discovery enriches the narrative of cosmic evolution, illuminating the pathways of stellar genesis and the intricate processes that unfolded in the universe's formative years. Large-scale cosmic surveys provide essential tools for unraveling the complexities of the early universe. These expansive observations map vast regions of the cosmos, gathering immense quantities of data that reveal the distribution and properties of galaxies, clusters, and dark matter. By meticulously analyzing this information, scientists can reconstruct the conditions that prevailed during the universe's infancy, shedding light on the formation of the first stars. Detailed examination of galaxy formation allows for insights into the density fluctuations that initiated the gravitational collapse, triggering the birth of stellar bodies. The surveys capture light from distant galaxies, allowing for the estimation of their redshifts, which in turn informs the timeline of cosmic expansion. This chronology establishes a clearer picture of how structures emerged from the primordial gas clouds, evolving into the complex web observed today. Key instruments, such as advanced telescopes and spectrographs, enhance the ability to detect faint signals from these ancient sources. By cataloging the various wavelengths emitted, researchers can estimate the chemical compositions and masses of early stars. This data is crucial for understanding how these stellar objects influenced their surroundings, contributing to the reionization of the universe and the eventual emergence of galaxies. The cumulative findings from these extensive surveys continuously refine theories surrounding the genesis of the universe, providing clarity amidst the vastness of cosmic history. The expansion of the universe presents a profound framework for measuring cosmic distances. Redshift serves as a critical tool in this endeavor, revealing the movement of celestial bodies away from Earth. As light travels through expanding space, its wavelength elongates. This phenomenon, known as redshift, provides a direct correlation between distance and the velocity at which objects recede. Observations of distant galaxies employ this principle, allowing astronomers to assess their position within the ever-expanding fabric of the cosmos. The greater the redshift, the further these galaxies are situated. This relationship not only aids in mapping the universe's structure, but also offers insights into its age and the rate of expansion. The Hubble Space Telescope has significantly enhanced these measurements, capturing light from galaxies billions of light years away. Each observation contributes to a comprehensive understanding of cosmic evolution. Shifts in redshift data also illuminate the influence of dark energy, a mysterious force accelerating the universe's expansion. Miliaconde in Gwedi Ixi, the cosmic microwave background radiation, provides a snapshot of the universe's early state. Together, these elements construct a cohesive model of a dynamic cosmos, ever-changing and unfurling across the expanse of time, revealing the intricate web of connections that define its existence. The Hubble Space Telescope has played a pivotal role in advancing the understanding of stellar astronomy. Its position above Earth's atmosphere allows for clear, uninterrupted observations of celestial objects, free from atmospheric distortion. This clarity has enabled scientists to investigate the formation and evolution of stars with unprecedented detail. One significant contribution lies in the ability to capture high-resolution images of distant galaxies, revealing the processes of star formation within their spiral arms. The telescope's observations have shown that massive stars, often forming in clusters, emit powerful stellar winds and radiation, influencing their environment and the formation of additional stars. Hubble's ultraviolet capabilities have provided insights into the life cycle of stars, from their birth in nebulae to their eventual demise as supernovae or remnants such as white dwarfs and neutron stars. These observations have allowed for the measurement of key parameters, including stellar masses, temperatures, and chemical compositions, enriching the understanding of nucleosynthesis, the process by which elements are forged in the cores of stars. The telescope has also contributed to the study of exoplanets, identifying the atmospheres of distant worlds. By examining the starlight filtered through these atmospheres, it has provided clues about their compositions and potential habitability. Each discovery enhances the broader understanding of the universe's evolution and complexity. The emergence of quasars marks a pivotal moment in cosmic history. These extraordinarily luminous objects serve as beacons from a time when the universe was still in its infancy. Formed around supermassive black holes, quasars radiate energy that can outshine entire galaxies, illuminating the vast dark voids that once prevailed. Their intense emissions provide crucial insights into the conditions of the early universe, acting as both markers and catalysts for understanding early star formation. This period, often referred to as the cosmic dawn, was characterized by the rapid assembly of gas, dust, and dark matter as gravitational forces coalesced material. The first stars ignited, initiating a sequence of events that would shape cosmic evolution. Quasars reveal the environments surrounding these young stars, shedding light on the interplay between black holes and their host galaxies. Observations indicate that as these quasars formed, they influenced their surroundings, driving massive outflows of gas and regulating star formation processes. The feedback mechanisms established during this era contributed to the gradual buildup of galaxies. This interplay between massive black holes and early stellar populations illustrates the interconnected nature of cosmic phenomena, highlighting the intricate relationships that define the evolution of the universe over billions of years. The emergence of massive black holes in early galaxies significantly influenced their formation and evolution. These enigmatic entities acted as gravitational anchors, drawing in surrounding gas and dust. The accumulation of material not only fueled their growth, but also stimulated star formation in the surrounding regions. This interaction led to the rapid emergence of stars, creating clusters that lit up the previously dark cosmos. In many instances, the energy released from accreting matter around these black holes heated the surrounding gas. This heating process prevented further star formation in certain areas, effectively regulating the growth of galaxies. The balance between star formation and black hole activity determined the structural dynamics of these nascent systems. Observations indicate that the mass of black holes correlates closely with the mass of the galaxies that harbor them. This suggests a co-evolutionary process, where the growth of stars and black holes influenced each other, shaping the overall architecture of the universe. The radiation emitted by these early black holes also played a crucial role in reionizing the universe. As the first stars ignited, their light, combined with that of the black holes, helped to ionize hydrogen gas, facilitating the transition from the cosmic dark ages to a more transparent state. This transformation set the stage for the complex celestial landscapes that would eventually follow. The transition from opaque to transparent unfolded over a vast expanse of time, marking the epoch known as reionization. Within this period, the first stars ignited, their nuclear fusion processes releasing immense quantities of light and energy into the surrounding cosmic fog. This illumination initiated a profound chemical reaction, influencing the very fabric of the early universe. The emergence of these luminous bodies generated ultraviolet radiation that began to interact with the hydrogen atoms that filled the cosmos. This interaction resulted in the ionization of hydrogen, stripping away electrons and creating a state of plasma. As more stars formed, a cascade of ionizing photons permeated the dark regions, gradually clearing the once dense medium. The subsequent expansion of this ionized region fostered an environment conducive to the formation of galaxies. Over several 100 million years, pockets of transparency developed, allowing light to travel freely across vast distances. Fluctuations in density contributed to the formation of larger structures. Observational evidence suggests that this process varied across regions, with some areas reionizing earlier than others. The intricacies of these dynamics reveal the complex interplay between stellar activity and the evolution of the cosmos, laying the groundwork for the rich diversity of galaxies and cosmic structures that followed. Observational evidence from the James Webb Space Telescope sheds light on the early universe, providing critical insights into the formation of the first stars. This advanced instrument captures infrared wavelengths, revealing celestial objects obscured by cosmic dust. The ability to peer into this veil allows for the identification of primordial galaxies, illuminating the conditions that prevailed during the universe's infancy. Images obtained from this telescope demonstrate the presence of massive stars forming in dense regions of gas. These formations suggest an environment rich in the necessary elements for star development, consistent with the predictions of cosmic evolution models. Data indicates that some of these early stars may have been significantly larger than those found in the contemporary universe, influencing the surrounding matter through their intense radiation and subsequent supernova events. Spectroscopic analysis provides further evidence of the chemical compositions of these ancient objects. The detection of elements such as hydrogen, helium, and trace amounts of heavier elements supports theories of nuclear synthesis that occurred in the hearts of these stars. The remnants of their explosive deaths contributed to the enrichment of the interstellar medium, fostering conditions conducive to the formation of new stars and planetary systems. The findings from the James Webb Space Telescope contribute to our understanding of the processes that shaped the universe, revealing the steps that led to the vibrant cosmos observed today. The timeline of the epoch of reionization marks a significant transition in cosmic history, occurring approximately 200 million to 1 billion years after the Big Bang. This period was characterized by the gradual ionization of hydrogen gas, as the first stars and galaxies emerged from the primordial fog, transforming the previously opaque universe into one filled with light. Radiation emitted by these early celestial bodies played a pivotal role in this process. It interacted with the surrounding neutral hydrogen, stripping electrons away and thus producing a predominantly ionized intergalactic medium. This shift led to the formation of the ultraviolet background radiation that permeates space today. Observations indicate that reionization was not a uniform event. Fluctuations in density and temperature among different regions resulted in varied timelines across the universe. Some areas experienced reionization earlier than others, suggesting a complex interplay between massive stars, black holes, and the surrounding matter. Understanding this epoch provides insights into the evolution of structures within the universe. It highlights how the interplay between radiation and matter influenced galaxy formation and growth. The implications extend beyond mere chronology, allowing researchers to piece together the conditions that fostered the emergence of diverse cosmic phenomena observable in the contemporary universe. Each finding adds depth to the ongoing exploration of cosmic history, revealing the intricate processes that shaped existence. Stellar winds play a crucial role in shaping the intergalactic medium, a vast expanse permeated by low-density gas and dust. These outflows, propelled by the intense radiation and energy emitted by massive stars, carry essential elements into the surrounding environment. This process not only enriches the medium with heavier elements, but also influences the temperature and density of the gas present. As stars reach the end of their life cycles, they expel material through these winds, generating turbulence in the intergalactic medium. This turbulence fosters mixing and distribution of chemical elements, creating pockets of varying composition and temperature. The interaction of these winds with existing gas can lead to shock waves, further propagating energy and affecting star formation in nearby regions. In regions where stellar winds are particularly strong, the energy can create bubbles of hot gas, expanding outward and displacing cooler material. This phenomenon contributes to the dynamic nature of the intergalactic medium, where flows of gas and energy continuously interact. Observations indicate that these interactions can trigger the formation of new stars, as regions of gas become compressed and heated, leading to gravitational instabilities. Understanding the impact of stellar winds thus illuminates not only the life cycle of stars, but also the broader processes that govern the evolution of the universe itself. Each interaction reveals the interconnected nature of cosmic events, emphasizing the delicate balance within the vastness of space. Chemical enrichment began as the first generations of stars ignited, transforming primordial hydrogen and helium into heavier elements. This process, known as nuclear synthesis, occurred within the stellar cores, where temperatures and pressures reached staggering levels. It is within these stellar furnaces that elements such as carbon, oxygen, and iron emerged, laying the foundation for subsequent cosmic evolution. Supernova explosions, the violent ends of massive stars, propelled these newly formed elements into the surrounding interstellar medium. This region, once barren and devoid of complexity, began to evolve as the remnants of these stellar deaths enriched the gas and dust, creating a fertile environment for new stars and planetary systems. The evolution of galaxies was profoundly influenced by this chemical enrichment, leading to increased metallicity that allowed for the formation of rocky planets and, eventually, the conditions necessary for life. The presence of heavier elements prompted the development of complex molecules, fostering a chemical landscape rich in possibilities. As generations of stars continued to form and die, they contributed to a cascade of enrichment, creating a dynamic interplay of elements throughout the universe. This cycle of birth, death, and rebirth forged a diverse cosmic landscape, setting the stage for the emergence of galaxies, stars, and their formation. Theoretical astrophysics seeks to unravel the mysteries of these celestial bodies, employing innovative techniques to enhance understanding. Virtual observations play a crucial role in this endeavor, bridging the gap between complex models and tangible data. Simulations create a digital framework that mimics the processes occurring in the universe, allowing researchers to explore scenarios that are otherwise impossible to observe directly. This methodology aids in visualizing the intricate dynamics of gas clouds, stellar formation, and gravitational interactions, illuminating their underlying mechanisms. Advanced computational models generate vast datasets, which can then be analyzed through virtual telescopes. These telescopes synthesize information from various wavelengths, constructing a more comprehensive view of cosmic phenomena. The interplay between theory and observation fosters a deeper comprehension of the primordial conditions that led to star formation and galaxy evolution. The findings derived from these virtual explorations are not merely academic. They inform our understanding of dark matter and dark energy, fundamental components shaping the universe's structure. Insights gained through these simulations influence both observational strategies and theoretical frameworks, underscoring the symbiotic relationship between virtual observations and astrophysical inquiry. In this continually evolving field, the synthesis of simulation and observation propels the quest for knowledge, guiding humanity's understanding of the cosmos and its enigmatic origins. The connection between dark matter and stellar evolution reveals a profound interplay that shapes the structure and evolution of the universe. This elusive substance, constituting approximately 27% of the universe's mass energy content, exerts gravitational influence that governs the formation of galaxies and star clusters. The presence of dark matter serves as an unseen architect, determining the pathways through which ordinary matter collapses and coalesces into luminous entities. In regions of high dark matter density, gas and dust accumulate more efficiently, fostering conditions conducive to star formation. The gravitational pull from dark matter halos accelerates the collapse of these primordial gas clouds, initiating the processes that, as stars evolve, they contribute to the cosmic cycle, enriching their surroundings with heavy elements forged in their cores. This enrichment alters the dynamics of subsequent star formation, emphasizing the interdependence between dark matter and stellar evolution. Over cosmic time, this intricate relationship continues to shape the architecture of the universe, revealing the delicate balance between the unseen forces of dark matter and the luminous objects that illuminate the vast expanse of space. The first stars served as catalysts for galaxy formation, their formation marked by the gravitational collapse of primordial gas clouds. These early luminous bodies ignited nuclear fusion, emitting light and heat that transformed the surrounding environment. The intense radiation from these stars contributed to the reionization of hydrogen gas, allowing photons to permeate and alter the state of matter in their vicinity. As these stars aged and eventually perished in supernova explosions, they released heavy elements into the interstellar medium. This enriched material became the building blocks for subsequent generations of stars and galaxies, fostering a dynamic cycle of creation and destruction. The remnants of these initial stellar explosions led to the formation of denser regions in the gas, where gravity could once again dominate, triggering new cycles of star formation. The symbiotic relationship between these ancient stars and the evolving galaxies illustrated a complex interplay. The gravitational pull of forming stars contributed to the aggregation of matter, leading to the spinning disks characteristic of galaxies. As structures coalesced, they began to exhibit spiral patterns, setting the stage for the diverse formations observed in the universe today. In this vast cosmic arena, The emergence of the first stars laid the groundwork for the rich variety of celestial structures that populate the universe, defining its evolutionary path. These cosmic filaments, vast structures of dark matter and gas, played a pivotal role in shaping the early universe. They served as the scaffolding upon which matter accumulated, guiding the gravitational interactions that led to star formation. Within this interconnected network, regions of higher density emerged, fostering the conditions necessary for gas clouds to collapse under their own weight. As the filaments became denser, hydrogen and helium gas began to gather, creating vast reservoirs from which stars would eventually be born. The intricate interplay of gravity and pressure within these regions ignited the process of nucleosynthesis, fueling the birth of the first luminous objects. In this environment, the temperature and density reached critical thresholds, allowing nuclear fusion to commence. This phenomenon marked the transition from dark, inert matter into glowing celestial bodies, illuminating the surrounding darkness. The influence of cosmic filaments extended beyond mere star formation. They also facilitated the formation of galaxies by channeling gas and dust into more concentrated areas. Over time, these processes resulted in the diverse array of galaxies observed in the universe today, each with unique characteristics shaped by their initial conditions and the surrounding cosmic web. The legacy of these early structures continues to resonate throughout the cosmos, influencing the formation and evolution of stellar systems across vast expanses of time. Ionization marked a pivotal transition within the cosmic environment, as the emergence of the first stars emitted copious amounts of ultraviolet radiation. This radiation interacted with the surrounding hydrogen gas, stripping electrons away from their atoms. The result was a profound transformation of the interstellar medium, leading to a state known as reionization. During this epoch, regions once shrouded in darkness began to illuminate, with clusters of newly formed stars acting as beacons in the void. The ionized gas expanded, creating vast bubbles that altered the dynamics of the surrounding matter. These bubbles, expanding through the cold, dense hydrogen, encountered significant turbulence as they interacted with each other, shaping the structure of the universe. This reionization process not only influenced the immediate vicinity of the stars, but also had far-reaching implications for galaxy formation. The increased energy and radiation facilitated the growth of proto-galaxies, enabling them to gather mass and evolve into the galaxies observed today. In this newly energized environment, the interplay of ionized gas and dark matter began to dictate the pathways of cosmic evolution. The resulting balance of forces would lay the groundwork for the intricate web of structures that populate the universe, showcasing the interconnectedness of the processes initiated by those first luminous stars. Stellar population studies reveal profound differences between early stars and their modern counterparts. These ancient luminaries, formed shortly after the Big Bang, were primarily composed of hydrogen and helium. Their formation occurred in dense regions of primordial gas, leading to immense masses and rapid life cycles. This region witnessed the birth of massive stars, which burned brightly but briefly, often concluding their existence in supernova explosions. In contrast, contemporary stars exhibit a richer composition, with heavier elements forged in the nuclear furnaces of earlier generations. These metallicity variations create a distinct profile, influencing not only their physical characteristics, but also their evolutionary pathways. Modern stars tend to have longer lifespans and more diverse sizes, a reflection of the enriched interstellar medium from which they arise. Observations of stellar populations in galaxies allow for comparisons that highlight these differences. For instance, the Milky Way harbors remnants of those ancient stars, such as globular clusters, serving as relics of the early universe. Their study offers insights into nuclear synthesis processes and the chemistry of the cosmos. The transition from the first stars to contemporary stellar populations reveals an evolutionary narrative, underscoring the complexity of cosmic evolution. Each generation contributes to the ongoing cycle of star formation, shaping the universe as it evolves from a primordial state into a rich tapestry of stellar diversity. The formation of early galaxies hinged on stellar density, a critical factor influencing gravitational interactions within these nascent structures. In regions where gas and dark matter coalesced, the density increased, allowing for the emergence of stars. This concentration of matter initiated processes leading to the formation of the first galaxies, which would serve as the building blocks for larger cosmic structures. As these galaxies formed, their gravitational pull became a catalyst for further star formation. The energy released by the birth of new stars heated surrounding gas, creating pressure that regulated additional collapse and star formation. This interplay between stellar density and gravitational forces contributed to the complex architecture of the universe. The presence of massive stars in these early assemblies enriched the surrounding medium with heavier elements, paving the way for subsequent generations of stars and planets. The early universe bore witness to a significant transformation as these newly formed galaxies began to merge and interact. Such interactions fostered environments conducive to the rapid formation of stars, further amplifying the stellar density. Over time, this intricate dance of matter led to the diverse array of galaxies observed today. Each early galaxy, with its unique characteristics, played a pivotal role in the evolution of the cosmos, marking the transition from a dark, barren expanse to a vibrant, luminous universe. The Fisher diagram serves as a crucial analytical tool in understanding star formation rates within these early galaxies, because graphical representation illustrates the relationship between stellar mass and the rate at which stars are produced. It reveals how different factors influence the efficiency of star formation, offering insights into the underlying processes at play during the universe's infancy. Variations in the diagram highlight the diverse conditions present across regions of star formation. Denser regions, rich in gas and dust, typically exhibit higher star formation rates. Conversely, areas with less material reveal slower rates, indicating a dependence on environmental conditions. Such patterns suggest that the availability of raw materials is a dominant factor in determining the pace at which stars ignite. A star self-ignite. The data portrayed in the Fisher diagram also provides a glimpse into the timeline of cosmic evolution. By examining trends over billions of years, it becomes possible to infer the transition from predominantly massive stars to a more balanced population, including smaller, cooler stars. This transformation is essential for the long-term stability and chemical diversity of galaxies. Understanding star formation rates through this diagram sheds light on the processes that forged the first elements, influencing the chemical enrichment of the universe and setting the stage for subsequent generations of stars and planets. The legacy of these early formations remains imprinted in the very fabric of the cosmos. Understanding the life cycle of matter in the universe reveals a continuous process of transformation and rebirth. This cycle begins with the primordial elements, primarily hydrogen and helium, forged during the initial moments of cosmic history. These gases coalesce under gravity's influence, forming the first stars. Their ignition marked a pivotal transition, catalyzing nuclear fusion and generating heavier elements such as carbon, nitrogen, and oxygen. As these stars evolve, they undergo various stages, culminating in their demise, often resulting in supernova explosions. These cataclysmic events disperse elements across the cosmos, enriching the interstellar medium. This enriched material serves as the building blocks for subsequent generations of stars and planetary systems. Dust and gas clouds, now infused with heavier elements, collapse to create new stars, continuing the cycle. This process emphasizes the interconnectedness of cosmic matter, where remnants of ancient stars become vital ingredients for life's formation on planets. Within this vast expanse, solar systems form around newly ignited stars, and the potential for life emerges as organic compounds develop under specific conditions. The remnants of stellar evolution thus play a crucial role, illustrating the ongoing narrative of creation and destruction. Each cycle adds complexity to the universe, fostering an intricate web of existence. The search for exoplanets around early stars reveals a landscape teeming with potential. These stars, often characterized by their high temperatures and luminosity, create unique conditions for planet formation. Protoplanetary disks, rich in gas and dust, encircle these youthful celestial bodies, providing the raw materials necessary for planetary development. As the disks evolve, the gravitational forces within them guide the birth of planets, some of which may host the ingredients for life. Observations in this region showcase the diversity of exoplanets, ranging from gas giants to rocky terrestrial worlds. The atmospheres of these planets, shaped by their proximity to their parent stars, exhibit varying compositions and pressures. Some may have thick layers of hydrogen, while others could possess a more Earth-like atmosphere, capable of supporting liquid water. The methodologies employed in detecting these distant worlds include transit photometry and radial velocity measurements, enabling scientists to infer the presence of planets by observing the subtle effects they exert on their host stars. This meticulous process highlights the delicate balance between gravitational interactions and stellar radiation. As the search continues, each discovery contributes to a deeper understanding of the cosmos. The potential for life beyond Earth hinges on these findings, illuminating a path through the vast expanse of the universe's early epochs. The quest for knowledge persists, driven by curiosity and the desire to unravel the mysteries of existence. Dense environments, such as globular clusters and the early universe, facilitate unique stellar interactions. Within these regions, gravitational forces dominate, leading to frequent encounters among stars. These interactions can result in various phenomena, including mergers, ejections, and the formation of binary systems. The complex dynamics of these systems contribute to the evolution of stellar populations. Gravitational interactions create environments where stars can exchange energy and momentum. This exchange may allow one star to gain enough velocity to escape the gravitational pull of the cluster, while others may spiral inward, increasing their likelihood of collision. When two stars collide, the outcome can vary significantly, depending on their masses and velocities. Some may merge to form a more massive star, while others may break apart, creating a new generation of stars from the remnants. In these high-density settings, the rate of star formation can accelerate. Gas clouds can be compressed under the intense gravitational influence, leading to conditions favorable for new stars to ignite. This process highlights the interconnectedness of stellar life cycles, where the end of one star may give rise to new celestial bodies. Understanding these interactions provides insights into the formation and evolution of galaxies, revealing a universe shaped by both chaos and order. Stellar clusters emerge from the gravitational collapse of dense regions within molecular clouds. This process initiates a cycle of creation, leading to the formation of numerous stars in proximity to one another. Over millions of years, these stars undergo various stages of nuclear fusion, altering their internal structures and influencing their surrounding environments. The gravitational binding of these young stars allows for complex interactions, fostering the development of unique stellar populations. As time progresses, the dynamics within these clusters shift. Stellar evolution leads to the birth of massive stars, which burn brightly for a short period before exploding as supernovae. These events contribute to the chemical enrichment of the interstellar medium, seeding it with heavy elements. The remnants of supernovae, alongside other stellar remnants, interact with the remaining stars, driving further evolutionary processes. Eventually, the gravitational forces holding these clusters together weaken. Stars drift apart under the influence of gravitational interactions with neighboring clusters and the overall galactic gravitational field. This dissolution phase marks the end of a cluster's cohesive existence, resulting in a dispersal of stars across vast distances. Some stars may fall into the gravitational well of a nearby galaxy, while others become solitary wanderers in the vastness of space. The life cycle of stellar clusters reflects the continuous interplay of formation and dissolution, shaping the broader structure of the cosmos. The broader structure of the cosmos is intricately tied to cosmic web theory, which posits that galaxies and clusters are interconnected through vast filaments of dark matter and gas. These filaments serve as scaffolding for the formation of structures, dictating where matter accumulates and how it evolves over time. Regions of higher density attract surrounding material, fostering the conditions necessary for star formation. Through this process, gravitational forces draw matter together, forming the first galaxies and clusters. They emerge like pearls strung along the cosmic filaments, each contributing to the growing complexity of the universe. This gradual buildup results in a network of interconnected structures where the paths of light and matter intertwine. As stellar clusters evolve, they emit radiation that influences their environment, affecting nearby gas and dust. This feedback mechanism plays a critical role in regulating star formation across the cosmic web. Areas of high radiation may heat the surrounding gas, inhibiting further star formation, while in other areas, density fluctuations can lead to bursts of new stars. Over billions of years, these processes contribute to a rich and varied landscape of galaxies. The cosmic web stands as a testament to the universe's dynamic nature, illustrating how seemingly isolated events ripple through the vast expanse, influencing the evolution of all cosmic structures. Computational astrophysics plays a critical role in unraveling the complexities of the early universe. Through advanced simulations, researchers can recreate the conditions that prevailed during the formation of the first stars and galaxies. These simulations are designed to model processes that cannot be directly observed, revealing how gravity, gas dynamics, and radiation interact in the primordial cosmos. Insights gained from this computational approach allow scientists to explore the feedback mechanisms that govern star formation. In these simulations, the effects of radiation from newly formed stars heat surrounding gas, influencing the birth of subsequent stars. This interplay is essential for understanding the timeline of cosmic evolution, marking the transition from a dark, featureless universe to one filled with luminous objects. The data produced through these simulations also assists in identifying the characteristics of dark matter, which played a crucial role in shaping structures at large scales. By analyzing the distribution of matter and energy during various epochs, researchers can infer the underlying physics that drives cosmic expansion. Additionally, computational models facilitate the exploration of diverse scenarios, allowing for a range of conditions to be tested. The flexibility in modeling enables a better grasp of the complex interplay between the various forces at work. The role of supermassive stars in cosmic evolution remains a cornerstone of understanding the early universe. These colossal entities, often weighing hundreds of solar masses, possess the ability to influence their surroundings significantly. Their immense gravitational pull not only gathers nearby gas and dust, but also initiates the formation of galaxies. As these stars ignite, they emit massive amounts of radiation and energy, heating the surrounding medium and altering the chemical composition of the universe. The lifetimes of supermassive stars are dramatically shorter compared to their smaller counterparts, often lasting only a few million years. This brevity leads to catastrophic endpoints, resulting in supernovae that eject heavy elements into the interstellar medium. Such events enrich the surrounding environment, fostering the formation of new stars and planets. The remnants of these stars contribute to black holes, which can grow to supermassive sizes at the centers of galaxies. The feedback mechanisms generated by these massive stars shape the evolution of the cosmos, regulating star formation rates and influencing the growth of structures. This dynamic process underscores the significance of supermassive stars as not merely transient phenomena, but as pivotal agents in the ongoing narrative of cosmic development. Through their life cycles, they set the stage for the emergence of galaxies and the intricate web of matter that constitutes the universe today. Temperature and density play crucial roles in the processes that govern star formation. In regions of higher density, gravitational forces draw gas and dust together, creating clumps that can eventually collapse under their own weight. This gravitational collapse leads to a rise in temperature, as kinetic energy translates into thermal energy. The initial heating of these clumps is vital. It determines whether the material will continue to compress and form a star or disperse back into the surrounding medium. The temperature must reach critical thresholds for nuclear fusion to ignite in a nascent star's core. Initially, protostars exist in a phase where they radiate energy primarily through contraction rather than fusion. As gravitational pressure builds, temperatures soar to millions of degrees Celsius, enabling hydrogen nuclei to combine and form helium, releasing energy in the process. In contrast, lower density regions experience insufficient gravitational pull, making them less likely to ignite star formation. These areas remain dark and cold, contributing to the overall structure of the universe without giving rise to stellar bodies. The interplay of varying temperatures and densities across the cosmos leads to the formation of diverse stellar populations, each contributing uniquely to the evolution of galaxies. This nuanced balance shapes the cosmos, influencing the life cycle of stars and the environments in which they thrive. The link between gamma-ray bursts and early stellar events reveals critical insights into the energetic processes that shaped the infancy of the universe. These bursts, originating from the collapse of massive stars or the merger of compact objects, emit colossal amounts of energy, illuminating vast stretches of cosmic voids. They serve as markers in the timeline of stellar evolution, occurring in regions where primordial gas clouds once coalesced into the first stars. These early massive stars, often referred to as population 3 stars, possessed unique characteristics. Their composition, devoid of heavier elements, allowed for extreme fusion rates, culminating in violent supernovae. Such stellar deaths could trigger gamma-ray bursts, signaling the end of an era and the birth of new cosmic structures. In this context, they act as beacons, providing information about the conditions present in the early universe. Observations from distant galaxies indicate that these bursts occurred more frequently during the universe's youth, suggesting an environment ripe for rapid star formation. The remnants of these explosions contribute to the cosmic landscape, enriching the interstellar medium with metals and facilitating the formation of subsequent stellar generations. Through this intricate relationship, gamma-ray bursts not only illuminate the cosmos, but also narrate the story of its evolution, marking significant milestones in the grand scale of cosmic history. Theories of star formation delve into the mechanisms that govern the birth of these celestial bodies. Turbulent conditions present an environment characterized by chaotic movements of gas and dust, leading to the rapid collapse of molecular clouds. In such settings, gravitational instabilities arise, allowing for clumps to form and subsequently ignite nuclear fusion. This scenario often results in massive stars which have short lifespans and dramatically influence their surroundings through fierce stellar winds and supernova explosions. Conversely, quiescent conditions embody stability and a slower pace of material accumulation. Here, the gentle interactions of particles allow for the gradual coalescence of matter, fostering the birth of smaller, longer-lived stars. In these serene environments, the formation process facilitates the development of planetary systems, as the low turbulence permits dust to settle and form solid cores. Both pathways offer insights into the diverse range of stellar populations observed throughout the universe. Research continues to explore how these contrasting environments contribute to the overall structure of galaxies. The balance between turbulent and quiescent conditions can shape not only the type of stars that emerge, but also the evolutionary trajectories of entire star clusters. Each scenario leaves its mark, illustrating the complexity and dynamism of cosmic evolution. Understanding these processes remains vital for deciphering the history and fate of the universe itself. Galactic dynamics play a critical role in shaping star formation rates, influencing how regions of gas and dust coalesce under gravitational forces. The intricate interactions between stars, gas, and dark matter create environments that can either foster or hinder the birth of new stars. In regions where gravitational forces are strong, gas clouds can collapse more efficiently, leading to increased star formation. Conversely, in areas with less gravitational influence, the dispersal of gas can stifle the process. These phenomena manifest across varying scales. In smaller galaxies, star formation may be sporadic, driven primarily by local interactions. Larger galaxies, with their complex structures and diverse components, exhibit more regulated patterns. The gravitational pull from surrounding matter affects the density of gas clouds, determining the rate at which new stars emerge. Dense regions, often found in the spiral arms or central bulges, become hotbeds of activity. External factors further complicate this dynamic. Interactions between galaxies, such as mergers or close encounters, can trigger bursts of star formation. In contrast, the disruption of gas clouds by supernovae or active galactic nuclei can inhibit the formation process. Such events highlight the delicate balance these cosmic structures maintain, constantly shifting the landscape of the universe and shaping its ongoing evolution. Stellar population synthesis models serve as crucial tools in understanding the formation and evolution of galaxies. By simulating the effects of star formation and stellar evolution, these models provide insight into the complex interplay of various stellar populations over time. They analyze the light emitted by stars, allowing astronomers to infer the age and composition of distant galaxies. Each star, with its unique life cycle, contributes to the overall luminosity and spectral characteristics of a galaxy, shaping its identity. These models take into account numerous variables, including metallicity, star formation rate, and the initial mass function. The intricate calculations allow researchers to predict how light changes as stars age, transition, and die, emitting different wavelengths throughout their lifetimes. This emission is a key indicator, revealing the history of stellar populations and their contributions to the chemical enrichment of the interstellar medium. In regions where star formation is vibrant, young, hot stars dominate the light. Conversely, in older populations, cooler, redder stars become more prominent. By examining these spectral signatures, scientists can dissect the evolutionary timelines of galaxies, unraveling the mysteries of the early universe. Understanding these processes is essential, as they not only illuminate the past, but also inform predictions about the future evolution of cosmic structures. The interplay of cosmic events significantly influences local star formation, shaping the environments where new stars emerge. Supernova explosions create shockwaves that compress surrounding gas and dust, initiating the gravitational collapse necessary for starbirth. This process often leads to the formation of dense molecular clouds, regions where matter coalesces under its own gravity, fostering the conditions for stellar genesis. Galactic mergers further contribute to this phenomenon, as the collision of two galaxies results in bursts of star formation. The gravitational forces at play stir up existing gas, leading to increased density and the creation of new stars in rapid succession. This cyclical nature of cosmic events underscores the dynamic character of the universe, where destruction and creation coexist in an eternal rhythm. The remnants of these stellar processes, such as planetary nebulae and the remnants of supernovae, enrich the interstellar medium with heavier elements. These elements, in turn, serve as the building blocks for future generations of stars and planetary systems. Over time, this cycle fosters a diverse array of stellar populations, each with its unique characteristics and life cycles. Investigating these interactions enhances comprehension of the broader mechanisms governing galaxy evolution. These insights deepen the understanding of how local star formation is intricately connected to cosmic events on a grand scale. The unfolding narrative of stellar migration reveals its pivotal role in galaxy evolution. This phenomenon describes the movement of stars across vast cosmic distances, influenced by gravitational interactions and the dynamics of galactic structures. Over billions of years, these stars traverse different regions, altering their environments and contributing to the overall morphology of galaxies. In denser areas, interactions can lead to the formation of new star clusters, while in less populated regions, stars may disperse, creating voids that contrast with their surroundings. The interplay of these movements shapes the distribution of elements, affecting the chemical makeup of newly formed stars and planetary systems. Observations indicate that as galaxies merge or collide, stellar migration becomes pronounced, driving complex interactions. The gravitational pull from neighboring galaxies can lead to tidal forces that reshape stellar orbits, resulting in adjustments to the local star population. This constant shifting not only influences the structural integrity of galaxies, but also impacts their evolution. Younger star populations form in regions previously occupied by older stars, contributing to a timeline of stellar life cycles that reflects the history of the galaxy itself. Understanding stellar migration offers crucial insights into the evolutionary pathways of galaxies, providing a framework for interpreting the cosmos as a dynamic, ever-evolving entity. The cosmic dawn marks a pivotal epoch in the universe's timeline, occurring approximately 500 million years after the Big Bang. It signifies the moment when the first stars ignited, casting their glow across an otherwise dark expanse. This transition from darkness to light fundamentally altered the conditions of the cosmos, initiating processes that would lead to the formation of galaxies and larger structures. The emergence of these primordial stars generated immense energy, influencing the surrounding gas and dust. This radiation began to ionize hydrogen, a process essential for the evolution of the universe. As these early luminaries burned brightly, they enriched the interstellar medium with heavier elements through supernova explosions, setting the stage for future generations of stars and planets. Modern astronomy relies heavily on the study of this era. Observations of distant galaxies using advanced telescopes reveal signatures of these ancient stars, allowing researchers to piece together the formation and evolution of cosmic structures. Techniques such as gravitational lensing provide glimpses into the faint light of the cosmic dawn, illuminating the conditions that prevailed in the early universe. Data gathered from cosmic microwave background radiation further enhance understanding, offering insights into the temperature fluctuations that characterize this epoch. The ongoing exploration of these phenomena continues to refine our comprehension of cosmic evolution. Technological advancements are poised to revolutionize the observation of early stars, pushing the boundaries of what is currently known about the cosmos. Innovations in telescope design, such as large aperture arrays and space-based observatories, will enable astronomers to capture unprecedented detail in distant galaxies. These instruments will utilize advanced imaging techniques, allowing for the detection of faint light emitted by the earliest celestial bodies, which existed during the universe's formative years. Adaptive optics systems will help mitigate atmospheric interference, providing clearer and more focused images. This capability is crucial when attempting to study objects that are billions of light-years away, as their emissions can be incredibly weak. Spectrographs, equipped with high-resolution capabilities, will allow for the detailed analysis of light spectra, revealing the chemical compositions of these primordial stars. This data is essential for understanding not only the stars themselves, but also the environment in which they formed. In addition to ground-based technologies, space missions equipped with infrared and ultraviolet detectors are being designed to peer through cosmic dust. These missions will provide insights into the processes that govern star formation and the evolution of galaxies. As these technologies develop, a clearer picture of the universe's infancy will emerge, enhancing humanity's grasp of its origins and the fundamental forces at play in cosmic history. Early star formation marks a pivotal moment in the history of the cosmos, setting the stage for the evolution of galaxies and the complex structures that inhabit them. This emergence of luminous bodies transformed the surrounding environment, ionizing hydrogen gas and leading to the reionization of the universe. This process allowed photons to traverse vast distances, unveiling previously hidden realms and altering the cosmic landscape forever. The formation of these initial stars catalyzed the synthesis of heavier elements through nuclear fusion, enriching the interstellar medium. This enriched material served as the building blocks for subsequent generations of stars and planets. Understanding these dynamics is crucial, as they provide insights into the chemical evolution of the universe, influencing everything from galaxy formation to the emergence of life itself. The timing and efficiency of early star formation also challenge existing models of cosmological evolution. Observations and simulations reveal a complex interplay between dark matter and baryonic matter, suggesting that the gravitational influences of dark matter halos were instrumental in guiding gas clouds towards collapse. This relationship forms the bedrock of modern cosmology, highlighting the need for ongoing research to decipher the intricate web of forces governing the cosmos. Each discovery regarding early star formation reshapes the understanding of cosmic chronology, offering new avenues for inquiry into the universe's past and the laws that govern it. Stellar physics plays a pivotal role in shaping the evolution of galaxies. Within these vast collections of stars, the processes governing stellar life cycles dictate the chemical makeup and structure of their surroundings. When massive stars reach the end of their lives, they often explode in supernovae, dispersing heavy elements into the interstellar medium. This enrichment allows for the formation of new stars, which in turn influences the subsequent development of galaxies. But the dynamics of star formation are intricately tied to the gravitational forces present in these regions. Gas clouds collapse under their own weight, igniting nuclear fusion and giving birth to new stars. The energy produced during these processes can trigger further star formation or inhibit it, creating a feedback loop that governs the rate of galactic evolution. The influence of stellar remnants, such as neutron stars and black holes, also significantly alters the environment. Their gravitational effects can disrupt surrounding material, leading to new star formation in some areas while suppressing it in others. Observational data from various wavelengths continues to illuminate the complexities inherent in this interplay. Each discovery informs models that attempt to unify stellar evolution with the larger framework of galaxy formation. These models propose various scenarios regarding the conditions that led to the formation of the first stars, Early galaxies, primarily composed of hydrogen and helium, provided the raw materials necessary for stellar birth. In this pristine environment, gravitational forces began to collapse these elements into dense regions, setting the stage for ignition. It is within these regions that thermal pressure and radiation from early stars could influence their surroundings, leading to the gradual assembly of more complex structures. Theoretical frameworks suggest that the first stars exhibited unique properties, such as rapid rotation and significant mass, which would subsequently affect their life cycles. These massive entities are believed to have lived for only a short span, yet their explosive deaths contributed to the dispersal of heavier elements throughout the cosmos. Such events enriched the interstellar medium, paving the way for subsequent generations of stars and galaxies. Computer simulations play a crucial role in these explorations, enabling scientists to recreate conditions of the early universe. By manipulating variables such as density, temperature, and composition, researchers can observe the formation processes of the first stars and their impact on cosmic evolution. This understanding deepens the knowledge of how the universe transitioned from a homogeneous state to the complex structures observed today, allowing for a more comprehensive view of our cosmic origins. The significance of stellar mass distribution in the early universe illustrates the formation processes that govern the emergence of the first stars. It is understood that mass plays a critical role in stellar evolution, affecting everything from life cycle duration to the energy output of a star. In the nascent cosmos, variations in mass led to an array of stellar types, from the massive, short-lived giants to the smaller, more enduring stars. These massive stars, often exceeding several times the mass of the Sun, contributed significantly to the chemical enrichment of the surrounding regions. Their rapid fusion processes produced heavier elements, releasing them into the interstellar medium upon their explosive demise as supernovae. This cycle of creation and destruction laid the groundwork for subsequent star formation, enriching the gas clouds from which new stars would emerge. Moreover, the distribution of these early stars influenced the gravitational interactions that shaped large-scale structures. Clusters of stars coalesced into galaxies, driven by the gravitational pull of their mass. This complex interplay between mass and gravity not only determined the fate of individual stars, but also dictated the architecture of the universe. Understanding this distribution allows researchers to piece together the puzzle of cosmic evolution, revealing how the first luminous bodies set the stage for the diverse array of astronomical phenomena observed in later epochs. The emergence of supernovae plays a pivotal role in the formation of galaxies. These explosive end-of-life events contribute vast amounts of energy and materials into the surrounding medium. Such ejections enrich interstellar gas with heavy elements, essential for the birth of new stars and complex structures. The shockwaves generated by these explosions compress nearby gas clouds, initiating gravitational collapse and subsequent star formation. This region becomes a crucible for molecular clouds, catalyzing the very processes that lead to galaxy assembly. As stars ignite, they emit radiation that influences their cosmic neighborhood, fostering an environment conducive to further stellar birth. The energy from supernovae also regulates the temperature and dynamics of the intergalactic medium, offering a feedback mechanism that can either promote or inhibit star formation. Galaxies evolve through cycles of birth and death, as supernovae inject energy and material, while simultaneously clearing regions of gas. This cycle is essential for the ongoing development of galaxies, shaping their morphology and influencing their evolutionary paths. The distribution and frequency of these explosive events help delineate the characteristics of galaxy clusters, providing insight into the underlying physics governing cosmic structures. Understanding this relationship enhances our comprehension of the universe's history, illustrating how interconnected phenomena drive the cosmic narrative forward. The future of cosmic exploration holds promise in illuminating the fascinating origins of the first stars. Several missions are being designed to probe the depths of the universe, targeting the moment when hydrogen and helium coalesced into the first luminous bodies. These initiatives will utilize advanced technologies to capture light from epochs long vanished, shedding light on the processes that shaped early stellar formation. In this pursuit, space telescopes equipped with highly sensitive instruments are set to venture beyond the reach of existing observatories. The goal is to observe the faint emissions from these primordial stars, which were born in dense regions of gas. This light carries information about their composition, temperature, and the conditions prevalent during their formation. Because the James Webb Space Telescope, for instance, is poised to provide unprecedented views of the early universe. Its infrared capabilities allow it to peer through the cosmic dust that obscures earlier galactic formations, revealing the intricate details of star birth. Future missions, such as the European Space Agency's Ariel project, aim to study exoplanets formed in the wake of these early stars, offering insights into how these ancient luminaries influenced planetary systems. Each of these efforts contributes to a broader understanding of cosmic history and the evolution of matter, leading to the rich diversity seen in the present universe. The legacy of the first stars extends far beyond their brief existence. They served as the architects of the early universe, influencing the formation of subsequent structures. Their explosive deaths, through processes such as supernovae, enriched the surrounding gas with heavy elements, laying the groundwork for the formation of galaxies, stars, and planets. This enrichment catalyzed the birth of new stellar populations, each generation increasingly complex. The remnants of these ancient giants can still be traced in the spectra of distant galaxies. The chemical signatures reveal a lineage, linking the present cosmic landscape back to those primordial beacons. This region of the universe now showcases diverse structures, from sprawling spiral galaxies to dense clusters, all bearing the imprint of their progenitors. These remnants highlight a continuous cycle of birth and death, where each stellar generation contributes to the cosmic ecosystem. The interplay of gravity and radiation from these early stars shaped the distribution of matter, influencing cosmic web formation. Regions of higher density became sites for galaxy formation, while vast voids persisted, a direct consequence of gravitational dynamics initiated by those first luminaries. Understanding these processes allows astronomers to reconstruct the evolution of the universe. The influence of those first stars resonates through time, echoing in the structures that populate the cosmos today. The mechanisms driving early star formation remain shrouded in uncertainty. This period, known as the cosmic dawn, is characterized by an intricate interplay of factors that have yet to be fully understood. Observations indicate that primordial gas clouds, primarily composed of hydrogen and helium, underwent gravitational collapse. Yet the specific processes triggering this collapse are still debated. The role of dark matter is crucial. These invisible structures forming a cosmic web are believed to influence the density fluctuations necessary for star formation. Yet, the precise relationship between dark matter halos and the birth of stars in these primordial environments is still being investigated. Another aspect involves the cooling processes of gas. Without sufficient cooling, gas cannot condense to form stars. The presence of molecular hydrogen, formed under unique conditions, is thought to be essential. Understanding how this molecule emerged and facilitated cooling in the early universe is a key question. Observations from advanced telescopes provide glimpses of these early stars, yet the details surrounding their formation and evolution remain elusive. The study of these ancient celestial bodies offers a profound connection to the origins of the universe. Yet many unanswered questions linger. The quest to unravel the mysteries of early star formation continues, illuminating the enigma of cosmic history. This ongoing investigation into the origins of the first stars shapes our understanding of cosmic evolution. These stellar entities, forming from primordial gas and dust, played a crucial role in transforming the vast emptiness of the early universe into a more complex structure. Their emergence marked a significant turning point, introducing the first heavy elements through processes such as supernova explosions. Such events catalyzed the formation of subsequent generations of stars and planetary systems. Understanding their life cycle offers insights into the chemical enrichment of galaxies, which continues to influence star formation and the development of life in the universe. The lingering shadows of these ancient giants still fill the cosmos, offering hints of their existence through the light they emitted billions of years ago. Research initiatives employing advanced telescopes and observational techniques are relentless, peering into the depths of space to detect the signatures of the earliest light. They strive to bridge the gaps in knowledge, addressing questions surrounding the conditions that led to star formation. Each discovery, no matter how small, contributes to a broader comprehension of cosmic history.